Welcome back to the heat transfer, where we will deal today in convection and in radiation. Okay. Well, convection is a mode of heat transfer by actual motion of matter. It happens only in fluids, liquids and gases. Can be of two kinds. It can be natural, it can be forced. Well, just to learn about it, everybody has a notion of it, so I need not enlarge on that. People can speak for hours together. Heat a fluid in a container. So what happens? That the bottom parts of the fluid, this time there is a liquid, they come in contact with the source of heat, and as a result, the hot part at the bottom expands. It expands, it becomes less dense, the density goes down in comparison to the other parts in the same liquid. So what happens? This hot part rises due to buoyancy. You know about buoyancy? So, naturally, if it rises due to buoyancy, something has to take its place. And who will do so? The colder part. Okay. So, and this process, hot going up, cold coming down, hot going up, cold coming down, okay, this goes on and on. And this is nothing but the convection, okay, the actual motion of matter, and there is a bulk transport, okay. Now, this is just to tell you about it. Then we know about forced transport of matter, which has different temperature characteristics as compared to the environment. For example, forced air heating, cooling in the homes and offices. Often we know it, all of us know it. Human circulatory systems, okay, where then we have the cooling system in automobiles, this and that, many kind of things where we use pumps just to take away energy. For example, the case of nuclear systems where water is used for cooling, etc., etc. Okay, and then the function of the heart is to circulate the blood, okay, keep on doing so, etc., etc. What's the problem with, why do we often need that the heat should be removed? And the problem is that if the heat is not removed, then there will be accumulation of heat. And accumulation of heat means rise in temperature. Rise in temperature means that the enclosure that we have, the pressure may increase and the container may burst. Okay. So many things can happen one after the other. Okay. And there used to be an advertisement in Indian television, okay, and that used to be कि ज़्यादा खाएगी तो मोटी हो जाएगी, ज़्यादा खाएगी तो मोटी हो जाएगी, और मोटी हो जाएगी तो कोई फ़र्क नहीं पड़ता, तो फट जाएगी, और फट जाएगी तो कोई फ़र्क नहीं पड़ता, बस फ़र्क ये पड़ता है कि दीवारें गंदी हो जाएंगी. Okay, so similarly the accumulation of heat, if it is not done away with by means of forced transport of bulk matter, then many accidents may occur, and they do occur in the case of boilers, etc., etc. Okay. Now, natural phenomena of convection, they are like the winds, okay, because, and trade winds in particular, which in our part of the world, hemisphere, there is a transport of heat through the atmosphere by winds which flow there from the North Pole in our part of the hemisphere to the equator. Maybe there is one South Pole and equator, etc. So there are so many kinds of winds, okay. In northern part of India where I live, there is a Pachua, western wind, and then there is a Purvaya, which comes from the east part, okay, and people like it because it is in the rainy season. So there is a song which as kids we used to sing, Pavan kare so jara jhume aise jaise banma nache mor. Ram gajab tha ye purvaya. Okay, and in the morning, most of us at my age or even at your age, they love to get up early in the morning, go out in some grassy places for walking, etc. Then they have the morning breeze, which you call sabah. So these are some of the things, and particularly in the near the water bodies, by the change of temperature during the day and during the night, there are some cool breezes which are blowing, so it's very nice. You can read many things and you can ask many questions and understand the phenomenon of convection. So radiation is a means of transfer of energy from one place to another place, which are quite distant. There may be a material medium between them, and there may not be. So let's take a representative of the stars, and the nearest star, which is closely related to the Earth where we live, and the Earth goes around the Sun, and so do other planets. And it's quite far. How much far is that? It's about, I'll not say exactly 500 seconds, but this is about 500 seconds of the speed of the rays, the waves, which are radiated out of the Sun and through the vast vacuum of about the same distance, because the Earth's atmosphere does go only a few hundred kilometers where air is there, else between the Sun and the Earth it's all vacuum, something called nothing, okay. And this distance is, I'm writing not scientifically. Scientifically I could have written 1.5 into 10 to the power of 11 meters. Okay, let me write for you. 1.5 in the scientific connotation, in the scientific way of writing is 10 to the power of 11 meters. Okay. So this is a very huge distance, and the energy, heat energy or whatever kind of energy we talk about, it travels from the Sun to the Earth by means of what is known as radiation. The radiation comprises of different kind of waves, which we call E by M, electromagnetic. And the same rays, same waves, they reach us. They may have different forms: ultraviolet, visible, infrared, even X-rays are there, and many other things. And the same kind of things, they travel from other distant stars through vast evacuated space, where they hardly interact with material particles. This is one thing. So you understand what is radiation in a nutshell. All bodies, they emit, absorb, or absorb and scatter electromagnetic radiations of different kinds. Black is beautiful. Black is beautiful. What the poet says, "आ जाओ अफ्रीका, आओ बबर की चाल." Babar means the tiger. आओ बबर की चाल, आ जाओ अफ्रीका. These days we have Black Lives Matter movement. But black is really black is beautiful. White is the other end. When we look at the Vibgyor, violet, indigo, blue, green, yellow, orange, red. These are the various 7 colors that can be seen in a rainbow. And if all the colors, they are put together, and this experiment has been told to you in your junior classes, that when all the colors are rotated very quickly, then what appears to us is as if the sensation is that of white. White is the other end. Okay, these are all radiations. These colors, bodies show their color because particular, for example, blue is absorbed, okay, and the other colors are not. Colors I will tell you some other time, okay. White is the other end. Now, to those students, because this is already told to you in your high school classes, and there is something called color code. Color code. Color code of resistors. Of also there used to be color code in the case of capacitors, but definitely in the case of carbon resistors that are kutir udyog, small units where they couldn't have printing, etc., then the color code was there. There is no time now that I mention how the color code is done, but the color code is black, brown, red, orange, yellow, then green. 5, 6, this is blue, 7, violet, 8 is grey, which is the closest color to white, and this is 9. And in the decimal system, we need how many digits? 10. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the combination of these digits can give you any other digit higher or lower than 1. Of course, all things, all numbers are positive. So there is a way to remember that. because Bengal used to be ahead of the rest of India when I used to be a kid. Okay, so it came from Bengal that there was one gentleman by the name of Mr. B.B. Roy, and because for education in those days, for higher education in science and technology and even otherwise, to become a barrister, etc., people used to go to the Great Britain. We were a colony of Great Britain. So Mr. B.B. Roy, he went to Great Britain, and there he found a very good wife. Okay, but later on I learned that Great Britain is famous for its villas, dwelling places, okay, houses. Food is very good in the Orient, India, China, in the subcontinent, etc. And the wives are very good in Germany. German wives are Egyptian wives. So one of my Chinese friends, when I was visiting the People's Republic of China, he told me one day, Mr. Rizvi, because they couldn't say at that time Rizvi. So he will say, Mr. Rizvi, you know, I have a US wife, okay, and so the food is no good in my home, and I have I live not in China, but I live in the USA. The only thing, yes, the wives are beautiful, good wives are found in Germany and Great Britain, and maybe your mother will be very unhappy with you when you tell that, okay, and good houses in the Great Britain and good salaries, fat salaries in the United States of America, which used to be people's American dream, okay, the dreams of United States of America, I don't know what are they. Anyway, so for example, these are the summer times when we must wear light clothes. In the winter times, our clothes should be close to black the beautiful, because black body is a good absorber as well as it is a good emitter of radiation. Just to mention, before I go and talk to you about cooling, and that is Newton's law of cooling, I'll deal the last thing today. Dewar flasks, thermos, silver coated double walled glass vessels, evacuated between the two layers. You have used that. Your parents use that. Your mothers definitely, to keep hot water or cold water these days. Okay, so next I'll talk to you about a law which is called Newton's law of cooling. Mr. Newton was not a good man. He gave so many things, he studied so many things, this law, that law, here, there, anywhere he could do. Okay, we talk about that. So come on, have a cup of tea. Okay, my cup of tea is at moderately hot temperature just now, and if I keep it for some time, then it may get cooled down. This is the kind of thing what we are going to discuss in Newton's law of cooling. Of course, there was no tea or coffee at the time of Mr. Newton. Okay, so let's see. Newton's law of cooling deals in a small temperature difference between a hot body and its surroundings. not more than 80 degrees Celsius in any case. Because if the temperature difference between a hot body and the cold surroundings is much, then there is another law which is effective, and that is called Stephen's law of cooling. But Newton's law of cooling, it deals in the fall in temperature. And the genius of Newton, I said Newton was not a good man because anywhere Mr. Newton will come in the classical physics, because he studied almost all topics which he could. Anyway, in the Newton's law of cooling, we conduct an experiment, and the experiment is about a calorimeter with a hot liquid inside, fixed with the stirrer and the thermometer to take up its temperature, and then there is a double walled container which fixes the calorimeter over here. The temperature of T1 of the body is more than the temperature of the surroundings, and maybe we take a mass of water in the calorimeter which is about 300 grams, okay, equal to m. In fact, 300 ml also counts for 300 grams, novel temperature and pressure at which the experiment is conducted. The temperature of the water in the calorimeter is about 40 degrees above this temperature T1. Then of course there is a rate of loss of heat, Q for heat and T for time. So time rate of loss of heat, which is shown by minus dq dt, and this minus dq dt is proportional to delta T, that is T2 minus T2. So because there is a direct proportionality between this and this, therefore there is a constant of proportionality, and like all constants of proportionalities, the constant will not depend upon this variable, and constant will also not depend upon this variable. Okay, what does it depend on? As usual, it is the function of the system, and the system comprises of an area and the nature and this and that, and k is a positive constant. Okay, so when we build up our description, then we say that heat loss for a fall of temperature, say dT2, is equal to dQ. How much it will be? The mass multiplied by the specific heat capacity, S multiplied by dT2, the fall in temperature, the change in temperature. S is the specific heat capacity. So I can write my dQ. If I divide it by dt, then this turns out to be equal to ms dt2 upon dt. Okay. Or I can say that we arrive at an equation of kind minus ms dt2 upon dt is equal to k d2 minus t2 minus t1. So we solve this equation, okay, and obtain the result. The result is that if we keep on recording the temperature in this thermometer at an interval of say 60 seconds, that is 1 minute, then we find that the fall in the temperature, it goes like this, and that means initially the fall in temperature is more, and finally it becomes less and less and less. So from this equation, minus ms dt2 upon dt is equal to k T2 minus T1. Okay. So I write that dt2 T2 minus T1 turns out to be minus k ms upon ms into dt, which I can write as minus k dt, where capital K is equal to small k upon ms. Okay, the constant, the symbols have their meaning. Now from here to here, I change my variable to T2 minus T1, and I write T2 minus T1 upon T2 minus T1 is equal to minus KT. Okay. Why? The reason is that I can take this T1 to be a constant. So the change in the value of T2 minus T1 will be the same as the change in the value of T2. If so, then I have this as this is as here in dy upon y, dx upon x, okay, whatever, d Hasan Shahid upon Hasan Shahid, okay, and minus kd. Now when we integrate, then the integral turns out to be equal to log natural ln or log to the base e. I will tell you what it is. T2 minus T1 is equal to minus kt, because when the integration is carried out here, the integral dt is equal to t plus a constant of integration small c. Okay. So I can write T2 minus T1 is equal to the base of the logarithm, which is e, raised to the power of minus kt plus c. Okay, which I can write as e to the power of minus kt into e to the power of c. C is a constant, and I can write this e to the power of c is equal to constant c or c dash or whatever. Okay, so I get a relation that T2 minus T1 is equal to c e raised to the power of minus kt. Okay. Now what is e? E is the Euler's number, 2.71. Sometimes we write it as 2.72, but right now I am giving the number 2.7, 82, 81, 82, 84, etc. Okay. So this is a pure number. So E is equal to this. Okay. And I have just shown over here that if y is equal to 1 upon x, and we try to integrate this side with dx, integral y dx is equal to 1 upon x integral dx, and this I can write, this is another integration besides e, what I gave to you, that integral x to the power of n dx is equal to how much? X to the power of n plus 1 divided by n plus 1 with a big provided. What is that provided? N plus 1 is not equal to 0. This is the condition. And for x to the power of minus 1, this turns out to be equal to 0. That is why that formula is not applicable in this case. Now, if I get this relation, okay, so log natural of T2 minus T1, if I plot it as on the y-axis of a linear graph paper, then I get there is a linear relationship with k, and this constant over here is negative. That is why the slope that I will get will be negative. The slope is minus k is equal to minus k upon ms. Incidentally, I want to tell you something. that Newton is the 16th century man. Newton was dead a long time before Euler came, the Swiss scientist Euler came. Before this kind of thing was evolved, okay, that e to the power of x is like this, so e to the power of 1 will be equal to like this, etc. And that series were evaluated. Those of you who are interested, you can just go back to your mathematics textbook or consult Professor Google, okay, Google Baba as we say in Hindi, okay, and Google Baba will tell you about this Euler and Euler's constant, small e, which is a pure number, etc., etc. Okay, because it is a pure number, so I just want to tell you that e to the power of x, if I have any x, what is the dimension of x? X also has got to be a dimensionless quantity. So any power of e is a number itself. Okay, so it has been a pleasure. Okay, and in the meantime, my cup of tea has become cooler. Okay, and hope that you have enjoyed. Of course, Newton could only ask his assistants, or he did himself. Okay, I don't know, it was given before his papers were burnt by his cat or after that. Okay, so the story goes that Newton was such a genius that he asked his carpenter to make 2 holes in his door, and when the 2 holes were made, then carpenter charged him with the money that he for the labor, and but smilingly the carpenter asked him that, why did you ask me to make 2 holes? Then Newton told him, silly, I have 2 cats. One is a big one and the other is a small one. And you know, then when he smiled and told him why, even the bigger one can let the smaller one pass, then Newton told him, why didn't you tell me before? I'll not pay you for this. Okay, and for a long time there was a dispute between Newton and the other man, and you know, we call him a genius. I don't want to belittle Newton, but all geniuses are like that. They are fools at times, and some fools like us, they can become geniuses at times. I have enjoyed this. Hope you have also enjoyed. Bye.